I'm going to tell you, first time I tried limits of composite functions, it really got me. It took me some time to understand it, but once I saw this rule, it made things a lot easier. And that's this: the limit as x approaches c of f of g of x. You're going to go ahead and find the limit of the inner function, and then you really don't do the limit of f, the outer function. You're just going to find f at whatever that limit value is. So obviously, if limit of g of x doesn't exist, this is going to fail to work. The other thing, the part that got me was actually this key piece of data here, which tells you the limit as x approaches L of f of x equals f of L. So what this means is the limit has to exist for f of x, and the point has to exist, and they have to be the same thing. In other words, it has to be continuous at f of x. You can't have a discontinuity. You can't have like a hole in the graph or a jump for f, for the outer function. So let's just go ahead and take a look, and we'll see when that does apply. So h and g are graphed here. So let's go ahead. We're going to find the limit as x approaches -1 of h of g of x. So if you remember, we can rewrite this as h of the limit as x approaches -1 of g of x. So let's start with the limit of g. So looking at g, as x approaches -1, the limit is 3. The function's 2, but the limit is 3. So we're looking for h of 3 now, because this limit here is 3. And then h of 3 is 1. So what was I talking about earlier? You just have to make sure that the outer function h of 3, that it's continuous there. So we're not looking for the limit of h. We want to make sure it's continuous. We don't want to see a jump there. Like we wouldn't want to see the graph doing something like this, where it approaches it with a hole there and comes and does like that. You wouldn't answer with this value because it's not continuous, so that it's going to fail. The test, or the rule here is going to fail. So you don't want to see a jump discontinuity. You don't want to see a hole in the graph, and you don't want to see, anything crazy like that. But this is fine. It's just a regular graph. So boom, we're looking right there. H of 3, which is 1. There's another one similar to that for you guys to try. And then limit as x approaches -3 of g of f of x. So once again, I'm going to rewrite this outer function. It's going to be g of the limit as x approaches -3 of f of x. So let's start with this limit as x approaches -3 of f of x. So that's right here. Well, hey, that doesn't exist. Look at that. We can't come up with a limit for that f of x. So here we're just going to say it does not exist. Like I said, there's another one probably similar to that. Oh, maybe not. We'll see. That's the last one. Maybe I should go through these. Let me go ahead and go through these then. So I thought I had another example. So for this one, we'll have the limit as x goes to 0, g of f of x. Really ugly f there. Let me fix that. And so that becomes g of the limit as x goes to 0 of f of x. So let's start with f of x as we go to 0. So that's right here, which is -1. So we want g of -1. And g of -1 is right here. So that's just going to equal 4. And then the last one, let's take a look at this one. The limit as x approaches -2, h of g of x. It's equivalent to h of the limit as x approaches -2, g of x. So we're going to go ahead and find the limit of g of x. So down here, as we approach -2, that limit is 0. So we have h of 0. And if we go to h of 0, there you can see we have the jump discontinuity. So you're not going to answer with -1. Even though technically h of 0 is -1, it fails this test right here. We need this part to be true in order for this to work out. So this fails to begin with, so therefore this part right here will not work out. So we're going to have to say here that it does not exist. And that has to do with the limit as x approaches 0 of h of x does not exist. So because of that, this limit here does not exist either.